My program crashed with this error, out of memory. But this machine has 16 gigabytes of memory. And my program was allowed to use only 4 gigabytes. That is just 25%. And I never chose that limit. So I made a smaller test with a limit of 256 megabytes. Then I kept asking for more memory until Java finally said no. The program crashed after using 224 megabytes, but the machine still had 1924 megabytes free. The machine still had space, the program did not. So why not the rest? And what does this have to do with AI? Your program does not use the machine's memory directly. It runs inside Java, and Java creates a separate space for your program. That space is called heap. The heap is smaller than the machine's memory for two reasons. In the last episode, cleaning up 6 million living objects took 29 milliseconds. The bigger the heap, the longer it can take to clean. And your program is not the only thing running on the machine. So, Java keeps the heap smaller on purpose. Now, here's the part that surprised me. Nobody chose 4 gigabytes. A rule chose it. Give Java 1/4 of the machine's memory. So, I ran the same program 3 times, changing only that rule. First, a small limit. It crashed just below it. Then, the default quarter. It crashed just below that. Finally, half the machine. Same crash, much higher up. Same machine, same program, 3 completely different crash points. So, this limit is not a fact about your computer, it is a policy. And sometimes that policy is wrong. Give Java half of a small machine, and Java still needs memory outside the heap. A percentage does not care whether the machine is large or small. And that brings us to second question. Same problem, much bigger. An AI model is not a magic. It is a very long list of numbers. Each number says how strongly one thing affects another. You use numbers like this already, like exam 60%, project 30%. An AI model is the same idea with 7 billion numbers. Nobody typed those numbers. Training tuned them to trillions of wrong guesses. So, loading the model means loading all 7 billion numbers at 4 bytes each. 28 gigabytes before the model has written one word. And writing one word uses all of them. Then the next word uses them again. The maths does not run on your processor. It runs on the graphics card. Your processor is one clever worker. This needs billions of small sums at once. Now look at where that card actually sits. It is a separate board plugged into the motherboard, and it has its own memory chips right beside it. That memory is VRAM. Reading memory means moving it down a wire, and every wire has a speed limit. The card's own wire is wide. The plug is narrow. So there are only two situations. Watch. If all the numbers fit on the card, they cross the thin wire once. If they do not fit, the rest must keep crossing it for every word. 70 words a second against 4. Same card. The worker was never the problem. The wire feeding it was. A normal card holds 12 gigabytes. Our model needs 28. You cannot delete the numbers, but you can store each one with less detail. It's like rounding $99.99 to $100. 2 bytes instead of 4, and 28 becomes 14. 1 byte, 7. 7 fits. 28 never did. But every number is less precise, so the model is slightly worse. Bigger models are 70 billion numbers. At 2 bytes each, that is 140 gigabytes. No card you can buy holds that. So, companies load it once for everyone. You send words, words come back. The numbers never move. This is why AI is an API. 3 episodes, 1 lesson. Your program never gets the whole machine. Next time, the same query 10,000 times.